The purpose of a fluid system is to transmit power from one location to another. Fluid power is converted to mechanical power by means of an actuator. Cylinder actuators deliver a linear push-pull motion via a rod and piston within a cylindrical tube. A single-acting cylinder is a cylinder in which the working fluid acts on only one side of the piston. The other side of the cylinder utilizes a mechanical load, springs, compressed air, other cylinders, or the momentum of a flywheel to push the piston back in the other direction. This particular cylinder utilizes a spring on the non-fluid side. A single-acting cylinder produces linear motion in one direction. When a control valve directs fluid through the inlet port into the blind end, pressure builds up and generates a force on the piston. When the pressure buildup is large enough, the piston begins to move, extending the rod. This is called the forward stroke. When a control valve directs fluid out of the port, the fluid pressure is removed. The force of the spring pushes against the piston in the other direction, and the rod returns to the cylinder. This is called the retraction stroke. Single-acting cylinders are most often found in reciprocating engines, pumps, and hydraulic rams. A double-acting cylinder is a cylinder in which fluid acts on both sides of the piston. This type of cylinder can produce linear motion in two directions. A double-acting cylinder has two fluid ports, one on the blind end and one on the rod end. A directional control valve sends fluid through the blind end port while venting fluid out the rod end port back to the tank. Pressure builds up and generates a force on the piston, causing the extension stroke. When the directional control valve is shifted, it sends fluid into the rod end port, out of the blind end port, and back to the tank. Pressure builds up and generates a force on the other side of the piston, causing the retraction stroke. To determine the speed of a piston during extension and retraction, we must first determine the significant working areas. The full piston area is the side of the piston without the rod. This is the area that feels pressure as the piston extends. The next significant working area is called the net area. This area is the size of the full piston area minus the area of the rod. The net area feels pressure when the cylinder retracts. The speed at which the piston extends and retracts is calculated using the volumetric flow rate divided by the area for the incoming fluid. Since each side of the cylinder has a different working area, each side experiences a different speed. Let's assume that the volumetric flow rate is equal for each inlet. Because the rod takes up space within the cylinder, less fluid is required to fill that side. This means that the fluid can fill the rod end side more quickly than it can fill the blind end. Since the rod end side fills with fluid more quickly, the cylinder will always retract faster than it can extend. All the cylinders shown to this point have been single-ended. They have only one working rod. On special cylinders, two rods may be used. These are called double-ended cylinders. They have two rods, both attached to the piston, and each coming through an end cap. Double-ended cylinders work similarly to single-ended, but are used when a constant speed is required for both the extension and retraction strokes. Since the flow rate is the same and the piston areas are the same, the speed for extension and retraction is also the same. Due to their simple design, cylinders are used more often than any other type of actuator for industrial applications. Although their motion is linear, it can be converted to rotary motion by levers, racks, and pinions, or other means, making them one of the most versatile types of actuator. Many different types of pumps exist to assist fluid movement in a variety of systems. An external gear pump uses two gears rotating against each other to provide fluid movement. One gear is driven by a motor connected to a shaft. This is called the drive gear because it is driven by a motor, and it in turn meshes with and drives the movement of the second gear. As the gears rotate away from each other and come out of mesh, they create an expanding volume on the inlet side of the pump. This creates a vacuum at the inlet port, allowing fluid to flow into the pump. Then fluid flows into the cavities and is trapped by the gear teeth. As the gears rotate, a flow path is created around the outside of each one. Fluid trapped in the slots between teeth is carried around and discharged into the cavity with the outlet port. Meshing of the teeth in the center of the pump seals the outlet port from the inlet port. No fluid passes between the gears. The advantages of external gear pumps are their high speed and pressure, relatively quiet operation, and that their design accommodates a wide variety of materials. Disadvantages include bushings in the liquid area can become worn and that they have fixed end clearances. Internal gear pumps are exceptionally versatile. This type of pump has one inner gear which is inside a second outer gear. The inner gear has a shaft driven by a motor and has teeth that protrude outward. The outer gear has teeth that protrude inward toward the center of the pump. As the inner gear rotates, it meshes with and moves the outer gear. Liquid is trapped in the gear spaces and carried from the inlet to the discharge. A stationary crescent-shaped divider separates the intake and discharge portions of the fluid. Advantages of internal gear pumps are a smooth and almost pulseless flow, and slightly more horsepower for its size. Disadvantages are its higher cost, limited size range, low to moderate pressure ratings, and few sources of manufacture. A rotary vane pump is a positive displacement pump that consists of vanes mounted to a rotor. The vanes are on an off-center drive shaft. As the shaft rotates, the variable length vanes slide in and out to maintain contact with the pump housing. The tension in the vanes is maintained by either springs or hydraulic pressure. As the vanes rotate, they create chambers of varying sizes within the pump. Fluid enters at the largest chamber. As the vanes rotate and retract, the chambers get smaller, forcing fluid to exit through the discharge port. The advantages of vane pumps are that they can handle low viscosity fluids at relatively higher pressures, can dry run for short periods, and develop a good vacuum. Their disadvantages include complexity and their unsuitability for both high pressure and high viscosity fluids. Piston pumps come in many different forms. A swash plate is a device used to translate the motion of a rotate shaft into the reciprocating motion of a piston. Swash plate piston pumps have a rotating shaft connected to a cylinder block containing pistons, which are pressed against a stationary swash plate that sits at an angle to the cylinder. As the shaft rotates, the pistons move against the swash plate, causing them to reciprocate within the piston block. The pistons create a vacuum that forces fluid in during half a revolution and expels fluid during the other half. On the intake stroke, a spring ensures the pistons pull back and maintain contact with the swash plate, causing fluid to fill the empty cavity left behind. On the discharge stroke, the angle of the swash plate forces the pistons back inside the piston block and discharges the fluid. The greater the slant on the swash plate, the further the pump pistons move and the more fluid they transfer. Piston pumps, in general, are manufactured with closer internal fits than other pumps. This means that internal slippage can be less so that they operate with reasonable efficiency at pressures both too high or too low for the operation of other pumps.